We now move into the next major section, types of hydrocarbon reservoirs. In this part, we shift focus from geological structures to the behavior of the fluids themselves. Crude oil is not a single pure substance. It is a complex mixture of several hydrocarbon types along with inorganic impurities. This slide lists four major hydrocarbon groups: paraffinic hydrocarbons, naphthenic hydrocarbons, aromatic hydrocarbons, and asphaltene hydrocarbons. These components strongly influence fluid properties such as density, viscosity, volatility, and production behavior. That is why petroleum engineers must understand both geology and fluid composition. This slide connects three related ideas. First, the origin of reservoir rocks and traps. Second, the origin of the hydrocarbons stored in the pore spaces. And third, the types of reservoirs that are commercially important today. The phase diagram appears here because the behavior of reservoir fluids depends not only on composition, but also on pressure and temperature conditions in the reservoir. The Gibbs phase rule relates the number of degrees of freedom in a system to the number of components and the number of phases. In petroleum engineering, we often deal with systems containing gas, oil, water, and rock. A phase is a physically distinct state of matter with uniform properties, and degrees of freedom refer to independent variables such as pressure and temperature. This rule helps us understand why phase diagrams are so important in reservoir fluid classification. Here we see the phase diagram for a real hydrocarbon reservoir, which is much more complex than a single component system. Important features include the bubble point locus, the dew point locus, the quality lines, the Crick-and-Den-bar, and the Crick-and-Dentherm. These concepts help us understand when gas evolves from oil, when liquid condenses from gas, and how the fluid will behave as reservoir pressure declines. Based on the phase diagram, reservoir fluids are commonly classified into 5 categories: black oil, volatile oil, gas condensate, wet gas, and dry gas. Each fluid type has its own production behavior, and petroleum engineers must understand these differences in order to design efficient production strategies. This slide defines some key terms used in phase diagrams. The bubble point line is where the first gas bubble comes out of the liquid. The dew point line is where the first drop of liquid condenses from the gas. The critical point is where liquid and gas properties become identical. The Crick-and-Dentherm is the highest temperature on the phase envelope, and the Crick-and-Den-bar is the highest pressure. Understanding this terminology is essential before we classify fluid systems. A black oil reservoir starts with an initial pressure much higher than the bubble point pressure. When the pressure is above the bubble point, the oil is in an undersaturated state, meaning it can still dissolve more gas. When pressure falls to the bubble point, the first gas bubble appears. Below this point, gas begins to come out of solution, and the reservoir becomes saturated. In black oil systems, a large fraction of the hydrocarbon is recovered as liquid oil at the surface. A volatile oil reservoir is similar to black oil, but the initial pressure is much closer to the bubble point. Because the fluid contains more lighter hydrocarbon components, a small drop in pressure below the bubble point releases a relatively large amount of gas. As a result, volatile oil reservoirs produce more gas and less liquid at the surface than black oil reservoirs. A gas condensate reservoir has a reservoir temperature between the critical temperature and the crickendentherm. As the pressure drops below the dew point, heavier hydrocarbons condense as liquid inside the reservoir. This is called retrograde condensation. These liquids can block pore space near the wellbore and reduce gas productivity. This is why gas condensate reservoirs can be quite challenging to manage. A wet gas reservoir has a temperature above the crickendentherm, so the reservoir fluid remains in the gas phase during depletion. No liquid forms inside the reservoir itself. However, when the gas reaches the surface separator, some liquid condenses out. That is why it is called wet gas. The gas is dry in the reservoir, but liquid appears at the surface. A dry gas reservoir consists mostly of methane. As pressure declines, the system never enters the two-phase region, either in the reservoir or at surface conditions. This means the fluid remains gas throughout its production life. Because of this simpler phase behavior, dry gas reservoirs are generally the easiest fluid systems to model.